Yes, I don't know if there is any way for putting it full screen, but anyway, I think it's quite well visible anyway.
I think I can, at least in this way.
Yes.
It would be too large, I guess. Well, let us see.
What is most preferable for you? I mean, I think it's very well visible anyway, I think so.
I think that this one is
okay.
An average of the first and the full screen. Okay, so
okay.
If you agree, I will choose this one.
Okay, I think it's fine for us. So it's a pleasure to introduce Professor Marius Mantoiu from University of Chile, who's going to talk about the spectral result for pseudo-differential operators on locally compact groups. Please.
Thank you very much, and thank you for the invitation. So my intention is to present spectral results in which C-star algebra techniques are used to characterize the essential spectrum and the Fredholm properties of some pseudo-differential operators. So since this is a non-commutative conference, I choose to take a rather large framework, a general framework, in which the results are not very, very strong. So if I would do the same thing for groups which are more or less Rn or nilpotent groups, the results would be much stronger. But anyhow, since I don't have enough time to develop plenty of results with details, I will be quite vague and I will choose a general framework with rather restricted results. Okay, so what are the spectral quantities I would like to discuss? One of these is the essential spectrum of an operator. So I will focus on an operator, let's say bounded, but it is also possible to treat unbounded operators, in a Hilbert space. I recall you that the spectrum of the operator can be decomposed into a discrete part and an essential part. In the discrete part, you put the eigenvalues which are isolated and have finite multiplicity. The other part of the spectrum, which is more interesting for me, would be the essential spectrum, and it is connected with the fact that spectral projections around each point have infinite rank. And the connected concept is the one of a Fredholm operator, involving the dimension of the kernel and the co-kernel of the operator. And I recall you that both concepts are invariant under compact perturbations. And this can be put in various forms, but my favorite one is the following. The essential spectrum of the operator H, it is the usual spectrum of the image of my operator in the Calkin algebra, which is a quotient of the algebra of all the bounded operators by the ideal of the compact operators. And there is something similar for Fredholmness. A theorem of Atkinson tells us that H is Fredholm if and only if the image in the Calkin algebra is inverted. So this will be the objects I will focus on, but by similar techniques, you can also treat epsilon spectra, numerical ranges of various types, and you can also prove localization and non-propagation properties, which are a sort of estimates on the evolution group of the operator H, if it happens to be self-adjoint. So let me tell you first what is a general form of the result I would like to prove. So I will show you that under certain assumptions, there are operators, there is a family of operators, maybe I will call them asymptotic Hamiltonians, such that the essential spectrum of my operator H can be expressed as the union of all the spectra of these operators. And Fredholmness is also connected with these asymptotic Hamiltonians. H is Fredholm if and only if each operator is inverted. And of course, to make sense of this and to be useful, these operators has to come from somewhere. They have to be intelligible and maybe simpler than the initial Hamiltonian. We should connect them with a framework in which the operator is defined. Okay, so first very general abstract nonsense is the following. If you want to have such a result, you can get it by using ideals. Suppose that your operator H belongs to a C-star algebra, which is contained in the C-star algebra of all the bounded operators on the Hilbert space. And let us say that it contains the ideal of the compact operators. You would like to surround tightly this ideal of compact operators, which has its relevance in spectral theory, as I showed you, by a family of other ideals. And these ideals are called here chi A, and surrounding means in this case that the intersection of these ideals would be the ideal of the compact operators, hoping that each such ideal and each quotient by the ideal has some meaning and it can be used somehow. So now if you compute the image of the initial operator in each of the quotient by each of the ideals, this is a source for the family of asymptotic Hamiltonians. You can show that you have such results automatically. I'm cheating somehow because if you don't ask something more, you will need a closure here on the union of the spectra. And here, this invertibility should be uniform in a certain sense. The norms of the inverses should be uniformly bounded. But I will be quite vague about this. By some extra work, you can get really these results. If not, just allow here a closure, let's say. Okay, so doing this, you have to be very careful about how you choose a C-star algebra. If you try the whole C-star algebra, which will be very generous, hoping to treat all the operators, you don't get anything because there are no ideals inside. You know that there is a single interesting ideal in B of H, which is K of H, and there is no chance to get interesting ideals satisfying such an equality. Oh, sorry, I send you to formulas 3 and 4, which do not exist. Of course, I was referring to 1 and 2. Okay, so I want to apply this in a certain framework connected with non-commutative groups. And my operator will be obtained by a global quantization connected to a certain very general class of groups. So my groups would be admissible, they will be amenable, type 1 and locally compact. So I will not spend time describing amenability and type 1 property. Let me say that this is a natural class of groups for which there is a nice non-commutative Fourier transformation, and for which the unitary dual, which comes now, which is the family of equivalence classes of irreducible representations of the group, is a nice space. It is not very nice, it is generally very complicated, but it still has a Plancherel measure, so you can make good integration theory on such a space. And amenability was discussed by Professor Weiss previously. The type of pseudo-differential theory of quantization I would apply to this is an extension of the pseudo-differential calculi defined by Różański and his collaborators previously on compact Lie groups or on nilpotent Lie groups, on which you can say a lot. You can go very far, having a lot of properties and a strong formalism. So this was extended to the case of locally compact groups, which might not be Lie groups, unimodular of type 1, and the unimodularity condition is just for simplicity. So we could also treat the non-unimodular case, and my results here can also be adapted to this. So what is the operator? The operator is a sort of pseudo-differential operator given by this formula, in which you should see a generalization of the formula you have here, which is the usual formula for the Kohn-Nirenberg quantization. So it involves symbols which depend on a variable x belonging to the group and another variable belonging to the unitary dual. And this f of x and psi is supposed to be an operator in the representation space of the irreducible representation psi. So you have here integration over two variables. One belongs to the group. It is called y. The other one is psi. This is the Plancherel measure. This is the Haar measure of the group. You couple the symbol, which is operator valued, with the representation itself, psi, applied to a certain combination of the group elements. These are operators. I don't describe in detail the condition I asked over this. And you apply a trace to get a scalar object and to be able to define such operators. There are plenty of reasons to study these operators. This is not the Hermander quantization of a manifold. It is different. It has some advantages from certain points of view. It is very well adapted to harmonic analysis. And I would like to study properties of such operators. So you notice that if the group is abelian, everything here is scalar because the irreducible representations are just characters, one-dimensional. So you get here a character of the group, which becomes the usual exponential in the case of Rn. And the compact situation is also simpler because it involves the Peter-Weil description of the unitary dual in terms of matrices and with a discrete dual. Okay, so now where do we find interesting information about our operator? This will be found in the behavior of the symbol in the x variable. So I fix, or I almost fix the point psi. I might fix it almost everywhere. And I look at the dependence on the variable x. For simple types of symbols f, you could call this a coefficient, isn't it? If f is polynomial in psi, you will have here the coefficients depending on x. So the behavior of such a function will be encoded in what I will call coefficient algebras. And these coefficient algebras are by definition unital C-star algebras, which are bounded and uniformly continuous on G, and which contain the trivial part, which should be functions which are small at infinity. The ideal of continuous functions which are epsilon small outside a large compact set. And I ask uniform continuity because this algebra is abelian. Obviously, it does not contain all the information about the problem, and I will complete this information by adding translations of the group. And I need these translations to be continuous. And in addition, to be able to implement this non-commutativity, I ask the algebra to be invariant under translations. And these are notations. Theta is the action of the group on itself to the left by translations. And at the level of functions, you implement the translations in the usual way. So you just compose with the translation at the level of the configuration space. So I ask all the algebras to be invariant under such translations. And there is a result connected with the Gelfand theory of abelian C-star algebras, telling you that there is a one-to-one correspondence between coefficient C-star algebras, such translation invariant C-star algebras, and equivariant compactifications of the group. So the group is supposed to be included openly and densely as a subset of a compact set omega. And because we asked invariant standard translations, the left translations of the group extend continuously to this compactification. And the connection is the usual one. If you have the abelian C-star algebra, you compute its Gelfand spectrum and it will satisfy such a thing. On the contrary, if you have a compactification of the group, you can associate to this a C-star algebra of continuous functions on the group, which are restrictions to the group of functions which were continuous on the larger space. So you just ignored what's happening on the boundary at infinity. Okay, and with such a result, you have the following pseudo theorem. I call it a pseudo theorem because it is still very far from being clear what the input is. So I take a coefficient algebra and I assume that the symbol, which I will quantize, belong to this algebra at the level of the x dependence for each psi. This is still vague. I can be more precise. You also need some reasonable behavior in the variable psi, which I will not spell out now. And the result would be that you can compute families of asymptotic symbols, which once again are supposed to be simpler and easier to understand, such that the essential spectrum of my pseudo-differential operator can be described as a union of spectra of pseudo-differential operators defined by all these asymptotic symbols. And similarly, at the level of Fredholmness, the operator is Fredholm if and only if each of the asymptotic operators defined by asymptotic symbols are invertible. And there are other results, so we don't have time to discuss that. So now I will try to describe the way we construct the two ingredients, the family of indices I'm using here, and the symbols that define the asymptotic operators. And of course, we should find them it comes from the behavior at infinity of this function f, which is quite compatible with what was known about essential spectra of Schrödinger operators and things like this. So for the index set y, we start with the algebra of coefficients, modeling the behavior of the symbol at infinity. And it has a compactification, which is a group union with a sort of boundary at infinity. This boundary at infinity can be awful. It can be very, very complicated in complicated situations. And because of invariance under translations, you get a compact dynamical system. And I focus on the part at infinity. This is compact, Hausdorff. You can apply techniques of dynamical systems to it. And I'm interested especially in orbits and orbit closures. So each point comes with an orbit. And the closure of the orbit is more important than the orbit itself. It is denoted Q omega. And I recall you that many orbits can have the same closure for interesting dynamical systems. So this would be the object which serves to define one of the asymptotic symbols and one of the asymptotic operators. So you could take all the points and all the orbit closures, but you can spare a lot of redundancy by this definition. Define a sufficient family to be a family of points such that the orbit closures cover the boundary at infinity. So you have this equality. Union over this subfamily of orbit closures would be the entire boundary at infinity. So you don't need to make computations for all the points at infinity, not even for all the orbit closures, but just for the family which is enough to cover the boundary. Okay, now what are the asymptotic symbols? I fix a sufficient family, and for each psi irreducible representation, we ask that f, depending on x, be an element of this sister algebra, which is identified with continuous functions on the compactification. And you make an extension and restriction procedure. So you first extend the function to a function on the entire space, including the boundaries. This is included into the identification of the sister algebras. A is defined in such a way that this is possible. And then you make the restriction at one of the orbit closures. It is rather obvious that there is an equivalent formalism involving limits at infinity along nets or along filters, but I prefer this one. So you extended the function for fixed psi on the boundary at infinity, and you take the restriction to one of the orbit closures, which is in a certain sense indecomposable. And now you would like to construct from this function, once again, a function defined on the group time its unitary dual. And to do this, you use this formula. So on the orbit, the group acts. The group has a variable x, and for fixed element omega y on the orbit, you can go around the orbit translating with the group. Omega y is fixed, and now x becomes the variable. And you define a new symbol depending normally of x and psi in such a way. So psi is put here as before, and here you go around the orbit. Imagine that the orbit is somehow a torus, or a sort of generalization of the torus. You fix one point and you go with Rn around the torus, and you get once again a symbol which you can quantize. And you do this with, you can do this with any point in the boundary at infinity, getting an operator of such form, the same form as before, but you use here this restriction of the extension of the initial symbol. And this will be the asymptotic Hamiltonianist. Well, you could wonder what's happening if you change the points on the orbits. And the fact is that nothing interesting happens. The spectra are always the same. So you get two points, omega and omega prime, having the same quasi-orbit, although they might belong to different orbits, then the spectra are the same. And this does not imply unitary equivalence. If omega is on the same orbit with omega prime, the operators are unitarily equivalent. But this is not interesting enough. For all the quasi-orbits, the spectrum is constant by some C-star algebraic simple argument. Okay, so now I'm going to the proof of my pseudo theorem. Let us see what happens at the abelian part. I start with the compactification associated to my C-star algebra with simplified notations. It has an interesting part at infinity. And for every element in the sufficient family, let me define the ideal of functions on omega, which are equal to 0 on this compact quasi-orbit. It is obviously an ideal of the family of all the continuous functions, and the quotient by this ideal can be identified with all the functions living on this quasi-orbit, on the orbit closure. And now, since we asked the family to be sufficient, this means that these orbit closures cover the boundary, you can show that the ideal of functions which are small at infinity, the trivial one that we want to eliminate, which is connected with the compact operators, it is the intersection of this family of abelian ideals. If this is the case, you show immediately that the quotient of the algebra of coefficients by the trivial behavior, by the trivial functions which are small at infinity, can be embedded injectively into a product of such abelian C-star algebras, each one coming from an orbit closure. And this is done sending the function phi into the family of restrictions on all the quasi-orbits. Well, this is nice information at the abelian part, but of course you have to make it non-commutative to treat the full pseudo-differential operator. So now this is done by cross products, and I will not define cross product. Let me recall you, as Professor Weiss told you, that this is a C-star algebra incorporating in an interesting way the entire dynamical system. The group, the algebra on which you act with the group, and the action is implemented by a sort of relations between the algebra part and the group part. Technically, it is a certain completion of the space of L1 functions on G with values in A. So it is composed of functions on G times G, actually. Let us imagine that they are kernels of future integral operators. So now the previous embedding of a quotient propagates nicely in a functorial way to cross products. This is one of the nice properties of the cross products. So the quotient of the full cross product by the cross product you do with a restricted ideal of trivial functions at infinity. The cross product commutes with the quotient, and finally you get embedding into a product of other cross products in which the group acts only on each of the quasi-orbits. Okay, so this is abstract because these algebras are intrinsic algebras. They are not algebras of operators. You need a representation to put this into a Hilbert space. And this is a famous Schrödinger representation, which is faithful here because of amenability. And it sends elements of these C-star algebras, which are basically functions on G times G, into such integral operators. This would be an integral operator, but there is also a composition with a translation. I think that people in pseudo-differential theory would call this the right kernel of the operator. And a very nice result, which shows you why we did the quotient by this particular cross product, is that the Schrödinger representation sends isomorphically this ideal into the ideal of compact operators on the Hilbert space L2 of G, where the Schrödinger operator, the Schrödinger representation acts. So finally, after representation, you get this embedding. You have the Schrödinger operators associated to the cross product, quotient by the compact operators. This is included into a product of Schrödinger representation of simpler cross products. These cross products come from infinity, as I told you before, by extension and the restriction procedure. Okay, so now what is the connection with this this cross product with pseudo-differential theory? And the fact is that you just need to do a partial Fourier transformation to get pseudo-differential operators from the Schrödinger representation. So recall that the elements of the cross product were basically functions or kernels on G times G. And the symbols I would like to use in quantization are functions on G times the unitary dual of the group. These are the symbols. You have a Fourier-Plancherel transformation going from functions on the group to certain class of sections on the dual of the group. And if you compose with such a partial Fourier transformation, you switch from the Schrödinger representation to the pseudo-differential representation. So you can think that they are equivalent. And finally, what you can write after making this transformation is that the quantization of symbols which are partial Fourier transformation of this cross product, quotient by the compact operators, can be embedded into a product of, sorry? I guess that it's not connected to me. So you embed this into a product of pseudo-differential calculi, each one coming from the quasi-orbit at infinity. And if you look what's happening with your operator into this representation, you see that it is sent into a family of pseudo-differential operators, each one defined by the restriction at on the corresponding quasi-orbit. And to conclude, we apply this inclusion to get our spectral result, which is this one, just noticing that the spectrum does not change under monomorphism of C-star algebras. It remains the same. It is one of the very useful techniques in C-star algebras, and it comes from the fact that injective morphism of C-star algebras is isometric. And it also preserves spectra, consequently. So you get this, and you would get such a result automatically from this inclusion, with the exception of the fact that you need a closure here. But with some extra work, I can exclude it. I can show that the union is already closed. And for Fredholmness, you have the same thing. The operator is Fredholm if and only if it's image in the quotient by the compact operators is invertible. And this is equivalent in the direct product with invertibility of all the elements. So now I could stop here, or if not, I have 2 more slides on examples showing that in certain situations you can compute the orbits at infinity in non-trivial situations, and you can have rather concrete examples. So I'm not really aware of how much time I still have.
I think there is still a bit of time, so if you wish to go through the examples.
Okay, so very quickly, an example, a non-trivial example in which you have a certain idea about what the orbits at infinity are, is the family of slowly oscillating functions on G. So the functions for which if you subtract the function from the translation of the function, you get something which is small at infinity. And this is really non-trivial. It is very far of being small at infinity itself. For example, in Rn, all the functions which have radial limits, which are different in various directions, have this property. Or another way to see this, if the derivatives of the functions exist and they are small at infinity, the function is slowly oscillating. So let's say a cosine of a square root of x is a good example. It is not small at infinity, but its oscillations are larger and larger towards infinity. And the nice fact is that in such a case, the boundary at infinity that you get is formed of fixed points. So the orbits coincide with the quasi-orbits, and they are just points. So they are very easy to implement in the formula. And what you get finally is the fact that the asymptotic symbols only depend on psi. They do not depend on the variable x. This is consequence of the fact that you have a point here and the functions will become constant. And thus the asymptotic Hamiltonians are no longer pseudo-differential operators. They are very particular. They are invariant, left convolution operators. So for example, if your symbol was a sum between a sort of kinetic energy and a potential, what you get is quite concrete. The essential spectrum is the spectrum of the free operator, which is obtained by quantizing this symbol h, and which is just convolution by the Fourier transformation of h, plus limits coming from infinity, and at infinity the things are so simple that in fact you see the essential range of the potential V. You have all the points starting from the lim inf of the potential at infinity and going until the lim sup at infinity. And there are simplifications also in the abelian case. Now, what happens if instead of cosine of square root of x, I would like to multiply it with cosine of x and get a potential? If you think that the graph of the function is quite complicated, so cosine of square root of x is composed of oscillations which are slower and slower, but which still stay between -1 and 1. And upon this, you apply an extra oscillation by cosine of x. If you want to treat such a thing, you have to mix in a single C-star algebra of coefficients, slowly oscillating functions, let's say with almost periodic functions. And obviously, you can get things which are much, much more complicated than this one. Because both the components could be more complicated and you still do linear combinations and limits, and you still have computable situation. The almost periodic functions are coming with the Gelfand spectrum, which is a Bohr compactification, which is a minimal dynamical system which cannot be decomposed into smaller parts. And you can show, this is not so easy, that the boundary at infinity of this composed algebra, of this other sophisticated algebra, it is the product of the Bohr compactification and the part at infinity of the compactification associated with slowly oscillation. And the orbits are rather clear. So you have just to repeat the Bohr compactification for each point of the other compactification. So in this case, the asymptotic Hamiltonians are all purely differential, purely almost periodic pseudo-differential operators. If they happen to be periodic and if the group is abelian, you could apply Bloch-Floquet theory to make the results more concrete. So this would be all my talk, and thank you very much for your attention.
Thank you for your talk. Are there any questions?
Yes.
Please.
So the program that you outlined and also the mentioning of slowly oscillating functions reminds me a bit of the theory of limit operators. Is there where you basically take where we conjugate an operator acting on Rn by translations? Is that related?
Yes, it is related. So at a certain moment when describing the compactification and the procedure to obtain objects at infinity, asymptotic symbols and Hamiltonians, an almost equivalent formalism would be in terms of limits along nets or filters. And these limits, they are produced, as you said, by in an operator sense. So the formalist would be equivalent. I think that this point of view is somehow simpler, but the point is basically the type of Hamiltonians you are looking at. So I presented you a rather simple situation in which anyhow part of the results are new, especially because I can twist them by co-cycles, which allow me to introduce magnetic fields in relevant situations. And I did not have time to put them here. So anyhow, you get certain new results, especially connected with twisting and especially connected with the non-commutativity of the group. On the other hand, I can prove, and I already published results using groupoids, which are much more general than this one, but which were difficult to present in this context. So vaguely the formalism is the same, but you have to use groupoids instead of dynamical systems, which would include many other situations. For example, situations in which you have inverse semi-group actions on something, which are much more general than groups, which can be adapted to graphs, which are not Cayley graphs, which can be adapted to T-links and things like this. Or to Toeplitz type operators in which you cut inside into a symmetric problem, you cut out part of the theory. So we'll no longer have such type of pseudo-differential operators and cross products. You will have groupoids and still you can show such results. But I agree that this is basically connected with what is called the limit operator theory.
Okay, thank you.
Any other questions?
If I may, I am very impressed with the formula for the essential spectrum in the case of Rn. Could you maybe go back to just to keep in my mind the formula of the spectral yes, of the essential spectrum for one Fourier multiplier plus one potential?
Oh yes, it becomes quite concrete in this situation. It was a problem how to treat really pseudo-differential operators in which the symbol is not simplified in such a way. And still, I'm not sure that with the limit operator formalism, one can do such things. The problem was attacked also with without using C-star algebras, by using Weil sequences and things like this. But this depends a lot on how particular the symbol of the operator is. And let me tell you that you can have such results also for numerical ranges and epsilon pseudospectra and other spectral quantities, which were difficult to define here.
Okay. Thank you very much.
Thank you for the question.
Are there any other questions?
Maybe I've got a question.
Please.
Marius, do you have, say, an example on, I don't know, say a stratified group, which is in the spirit of the one on our end, which you showed us?
Mm-hmm. Well, maybe you notice that slowly oscillation is possible on any non-commutative topological locally compact group. So in principle, this includes what you say. Almost periodicity is also possible on each even non-commutative group. So these results in particular can be applied to your case. What can be done in addition in such a case is to use the strong formalism you have to push the results outside the realm of bounded operators. So if you have symbol classes of functions of Hermander type, you have large classes of operators. I did not say anything about this. And now they do not belong to C-star algebras, obviously. They are unbounded and very complicated. But you can apply such things to the resolvent family of the family of operators. So if you have a formalism which is strong enough to tell you about affiliation properties, it means how do you convert properties of your unbounded operator into properties of the resolvent, convincing the reader that the resolvent really belongs to such algebras of cross-product type, or after Fourier transformation of bounded pseudo-differential operators. You can propagate all the results to this. And this was done in simple situations for abelian groups because affiliation is rather complicated. I dare to say it is very complicated to extract the good property of the resolvent. So essentially you should know a lot about the symbol of the inverse in terms of the symbol of the operator, or let's say about the integral kernel. This is not yet done for groups as you mentioned, but it is worth doing because obviously what I showed you is less interesting in mathematical physics if you don't go to unbounded operators. And essentially elliptic situations, at least with symbols of class SM, should be converted into resolvents which can be controlled by such things. And I'm waiting for results. I will probably try to do such things in the future. Anyhow, on the other hand, for discrete systems and for étale groupoids, you have a lot of discrete situations which are still interesting and can be covered by the formalism.
Thank you.
Any other questions? Well, if not, I think we can thank Professor Mantoiu again, and I'd like to thank all the speakers of today for very interesting presentations, and let me hand over to the organizers.
Well, thank you very much, Alessio. Yes, I would also like to thank all of today's speakers once more on behalf of the organizing committee. And I hope it was an interesting day for all of you. And we will reconvene tomorrow morning at 9 o'clock Central European time.
For me,
then,
sorry.
No, please.
Just a pleasant morning.
Oh, yeah, well. So, so have a good afternoon.